Okay, we are headed into the thermodynamics portion of the semester. We're going to start with chapter 15 on temperature, heat, and expansion. I'm going to dismiss my image because I don't want it to interfere with the presentation. Uh, okay, let's get started here. And uh, this lecture will help you understand temperature, heat, specific heat capacity, and thermal expansion. And those last two subjects, we're going to get a little uh, more specific and also study the specific heat capacity of water and the thermal expansion properties of water, especially between 0 degrees Celsius and 4 degrees Celsius, because they have uh, special properties. Um, So temperature, a quantity that corresponds to the warmth or coldness of an object. Now, this fellow's using his fingers to check the hot and the cold. Uh, I've never known anybody that can stick their finger in a water that's at some intermediate temperature between freezing and boiling and say, oh, that's exactly 115 degrees Fahrenheit or uh, 32 degrees Celsius. I mean, it's a relative. Uh, you can't be precise just from your feeling. As a matter of fact, if you put your finger in a cold bath and then suddenly put it in warm water, it'll feel hot, even though it may be like room temperature. It's going to feel hot just because it's a relative feeling. Um, so to be precise, we measure it with a thermometer, whether it be a mercury-filled glass tube or an alcohol-filled glass tube. We measure using a thermometer. There's no upper limit, and it has a precise lowest value, and we'll look at that when we start talking about absolute zero on the Kelvin scale. Okay, the temperature of a substance is proportional to the average translational kinetic energy or random molecular motion in the substance. So in a gas, that's how fast the gas particles are bouncing to and fro, bouncing off one another, bouncing off the walls. They have kinetic energy, and that kinetic energy determines temperature. So the lower the kinetic energy, the lower the temperature. The higher the kinetic energy, the higher the temperature. A liquid, it's how fast particles slide and jiggle past one another. Those particles, those atoms and molecules, they're in motion, and they're, if you recall, kinetic energy is 1/2 mv squared. So the velocity, if you look at the 1/2 mv squared, the mass isn't going to change, but the velocity is going to change. So the faster it's going, the higher the kinetic energy, and the higher the temperature. Now, solid, how fast particles move as they vibrate and jiggle in space. Um, okay, a thermometer. A liquid thermometer measures the temperature by expansion or contraction of a liquid. It used to be mercury. If you see an old a lab thermometer that has silver uh, a silver uh, core in it, then it's probably mercury. Most likely, you're going to see it with a red alcohol solution, and that uh, that's how we read temperature. Readings occur when the thermometer and the object or substance in question reach thermal equilibrium, the same average kinetic energy per molecule or atom. In other words, if you put a thermometer in a cold ice bath, they eventually reach equilibrium. The warm temperature, let's say the thermometer is at room temperature, the warmth of the uh, thermometer will transfer uh, by heat. It'll transfer the its energy to the cold bath, uh, and once they come into equilibrium, you're actually reading the the temperature of the thermometer. Now, an infrared thermometer operates by sensing IR radiation. I know we all went through um, COVID, and I know back then, if I had to go to St. Philip's and uh, do an experiment to record for the online classes, they would meet me at the door and take my temperature using an infrared thermometer. They didn't stick a little thermometer in my mouth to measure it. They just used a little infrared thermometer. Okay, scales, temperature scales. You have the Celsius scale is the one we use in most often used in science. We do use the Kelvin scale, but we'll start with the Celsius scale. It's named after Andres Celsius. It used to be called centigrade because there's a centi meaning 100. There's 100 gradations between the boiling point of water. I'm sorry, between the freezing point of water and the boiling point of water, and we used to call it centigrade. Now it's called Celsius. 0 degrees for freezing point of water, and 100 degrees Celsius for boiling point of water. Then there's a Fahrenheit scale, which we still use it. I mean, if you watch any of the weather, I mean, if you go down to Mexico, they're going to report the temperature in Celsius. If you're here in the United States, they're going to report it in Fahrenheit. And 32 degrees F is for the freezing point of water. 212 degrees F is for the boiling point of water. So you see that there's 180 degrees between on the Fahrenheit scale between the freezing point and the boiling point. In the Celsius scale, there's only 100 between the freezing point and the boiling point. And in some applications of science, we use the Kelvin scale, and named after Lord Kelvin. For freezing point of water, that's 273 K. It's not 273 degrees K. You don't say degrees. You notice there's no little circle the way we see in the Celsius and Fahrenheit scale. It's just 273 Kelvin for the freezing point of water and 373 Kelvin for the boiling point of water. Notice there's still 100 gradations between 273 and 373. So the scale is the same for Kelvin and Celsius, but it's just offset by 273. Well, what is zero? 0 Kelvin is absolute zero. That's the lowest temperature you can get, and they've reached microkelvin in the laboratory. But there's always still some jiggling going on. So I don't, even though we've reached microkelvin, we've never gotten to absolute zero, as far as I know. I could be wrong. So notice in the last line, kelvins rather than degrees are used. You don't say 273 degrees Kelvin, you just say 273 Kelvin. Okay, no, so you can see here 212 and 100. Those are both the boiling point of water. 32 and 0, that's the freezing point. We know 32 degrees Fahrenheit is 0 degrees F. There's a little one here. You can't really see it, but 98.6 degrees Fahrenheit is 37 degrees Celsius, and you can see it. It's right around there. It's a little hard to see. I was trying to put a little line on there, but I couldn't get it. So I was just using my cursor here. Where'd my cursor go? There it is. 98.6 body temperature is 37 degrees Celsius. Okay, now I've got a different scale here. Now this may be a little, I hope this doesn't confuse anybody. All this is how the scales go. There's another one that I didn't discuss on the previous slide because it didn't go that far, but minus 40 degrees Fahrenheit and minus 40 degrees Celsius are the same temperature. It's where the scales cross. Minus 40 degrees F is minus 40 degrees C. Now, again, in Fahrenheit, we have 32. Celsius, we have 0. Now, these are the same point. They're not, it's only the scale that's different. 98.6 is 37, and 212 is 100 degrees Celsius. Okay. Now, there's different kinds of motions in whether it's a gas, liquid, um, and solid. You do get some motion in a solid, but you get these vibrational motion where the components of a molecule kind of slide in and out, um, or they can rotate. Whoops, or they can translate. They can move, and it's the translational motion that gives us the kinetic energy that gives us our temperature. So remember that it's the translational motion that is the principal driving factor in temperature. Okay, now here's a little quiz. There's twice as much molecular kinetic energy in 2 liters of boiling water as in 1 liter of boiling water, which will be the same for both. Um, Twice as much molecular kinetic energy in 2 liters of boiling water as in 1 liter of boiling water. Well, the average kinetic energy is the same since it's uh, twice as much in 2 liters as there is in 1 liter. So the temperature is going to be the same. Average kinetic energy of molecules is the same, which means temperature is the same for both. Okay. To say that body A has a higher temperature than body B is to say that the body A has more internal energy, more mass, more kinetic energy per molecule, or more potential energy? Well, it's the kinetic energy per molecule. Since the relative masses of the bodies are not specified, we have no information about the relative internal energies. The temperature measures the average translational kinetic contribution to the internal energies, however. Okay, and that's the end of this first part. Um, we'll go on to heat in the next part. Oops, let's see.